In the design, development, and validation of autonomous vehicles, safety is of paramount concern. This means designers and engineers must consider and test a variety of overlapping systems and subsystems. Each is mission-critical to the automobile's safe operation. ANSYS has developed a comprehensive solution to address the system safety analysis, safe software development, and systems validation, with high-fidelity, physics-based simulation of the virtual world, traffic scenario descriptions, and sensor simulation. The following demonstration showcases the ANSYS self-driving safety solution. In this video, we show the development and validation of an autonomous driving system that is designed to keep the vehicle at a safe distance from any detected obstacles, such as other vehicles and pedestrians. This video covers functional safety analysis, embedded software development, closed-loop simulation, and hardware-in-the-loop testing. The process starts with functional safety analysis. This functionality is implemented with two path planning components and a selector, which passes through the first valid plan, either fully autonomously based on perception or adaptive cruise control to make sure a safe distance is maintained. We use this selector because the AI planner is not guaranteed to provide a safe plan. Functional safety analysis must be performed to ensure that the system meets the defined safety goals. ANSYS Medini Analyze systematically identifies the risks and hazards that could be caused by malfunctions of our system components. By applying safety analysis techniques such as fault trees in ANSYS Medini, we can derive functional safety requirements for the system. If an unsafe motion command is received, we first must prevent its execution, then provide a safe plan instead. The fault tree identifies the safety requirements necessary to meet the safety goal of avoiding collisions with pedestrians and are accordingly assigned the highest safety integrity level, ASIL-D. These functional safety requirements must be allocated to our system components, but not all of the requirements can be allocated based on the initial architecture. The architecture needs additional components to prevent an unsafe motion plan from being executed and to produce a safe plan. Now that we have designed a safe architecture, we can develop the embedded software used to implement the safing gates and adaptive cruise control functionalities of our system, according to the allocated safety requirements at ASIL-D. We can perform all the required software development, verification, and validation activities with ANSYS SCADE and leverage the automatic code generator, which is qualified for ISO 26262 compliant code generation up to ASIL-D. The adaptive cruise control ensures that the autonomous vehicle follows at a safe distance and speed behind other vehicles on the road. The safing gates and selector determines what happens if a pedestrian or any other obstacle is encountered in the planned path. We can now perform further safety analyses following the SOTIF standard, which expands on ISO 26262 and considers risks arising from the combination of sensors, software, and the interaction of those with the driver. For example, SOTIF analyses considers whether the system will work in varying weather conditions. This requires simulation. We now test the system with a closed-loop simulation in a virtual environment. With ANSYS VR Experience Driving Simulator powered by Scanner, we can create roads, virtual environments, and define vehicle dynamics and traffic. The next step is to simulate driving scenarios with an ego vehicle equipped with virtual sensors and vehicle dynamics. In ANSYS VR Experience sensors, camera, LiDAR, and radar sensors are simulated with high-fidelity physics. The scenario begins with the AI-based planner in control of the vehicle. We simulate a case where the AI-based planner mistakenly provides a plan that would cause a collision. The selector catches the error and switches over to the adaptive cruise control planner, which maintains a safe following distance. The car in front of us happens to turn right, and a pedestrian unexpectedly crosses the road in our path of travel. In this view, we are looking through the ego driver's view. Simulation makes it easy to rapidly test thousands of different conditions. For instance, varying the time of day, location, and road conditions. Here's the actual dashboard of our autonomous vehicle. We can see what the driver's view will be while traveling in the vehicle. This visual dashboard is created with ANSYS SCADE display, powered by the control code that we discussed earlier, created in ANSYS SCADE Suite. We can see that the autonomous vehicle starts in cruise control mode and is following the vehicle ahead of it at a set target speed and following distance. On the bottom of the screen, we can see 2D visualizations in terms of a point cloud and a top-down view of the same 3D LiDAR perception and ground truth data used by SCADE Suite. Although the AI is telling us to drive straight ahead, the safety gate detects that there is an object in the planned path and invalidates the plan. The selector chooses the next valid plan, which is the safing plan, causing the vehicle to brake at 100% to avoid a collision. We can see the pedestrian walking in front of the car on the depth and perception displays. The pedestrian clears the path of the vehicle, and the ego vehicle returns to the AI planner mode. Now let's add some variability. The top screen is the same scenario that we have seen earlier. On the middle screen, we have altered the road conditions so that the grip traction is less effective, like with an icy road or worn tires. With these new conditions, we discover that the algorithm does not work effectively and needs to be adjusted. On the bottom screen, we have added an additional safety gate limiting the maximum speed and throttle depending on road condition. At this point, the closed-loop simulation is complete. The next step is hardware-in-the-loop simulation. Now we need to validate how this system will behave on target. We can deploy and integrate the same embedded software components to a real-time operating system like Green Hill's Integrity, which has been certified to the highest levels for safety and security. This allows us to do full hardware-in-the-loop simulation with the real embedded target. This approach has shown how to successfully ensure systems and software safety of autonomous vehicles through functional safety analysis, embedded software development, closed-loop system simulation, and finally, hardware-in-the-loop simulation.